Hi everyone, welcome back to part 2 of my Capstone project, Redeployment Optimization at a Consumer Packaged Goods Company. To give a quick refresher on the problem which we're trying to solve, I work for a consumer packaged goods company, and demand for our products, that is, consumers demanding to buy products from the company I work for, has continually outpaced the supply at which my company can restock our products from our suppliers. So what we need to do is provide some recommended stock transfer orders, or STOs, from our supply chain network to meet that weekly demand and prevent shortages. Now, if you remember back to our last video, the approach we're going to take is to apply linear programming and an optimization algorithm with an objective function to minimize total cost, taking into account things like current inventory positions, current forecasted demand, current supply schedule, and all of the different inter-warehouse transportation modes, such as truckload or by railway, the times it might take to get from one distribution center to another, as well as the different costs associated with that. Now, last presentation I largely walked you through a PowerPoint, but this time I think it's going to be a little more interactive. I'm going to try and dive into the code and talk you through it that way. So I'm going to exit out of PowerPoint real quickly, and I'm going to go to Jupyter Notebooks. And what we're going to do here first is import some packages, right? So the first thing I'm going to import is pandas. Then I'm going to use the linear programming software or package, that Python provides called Pulp. Pulp has been really fantastic, and there's a whole lot of great material and documentation on what it does, and I'm happy to explain some of that more in a later video. And the last thing I'm going to import is Timeit. And I'll get to a little later on why I'm using Timeit, but it's just to show how quickly this optimization problem can be solved using Pulp and Python. So the first thing we want to do is import our data, and I'm going to be using CSV files. I have one for shipping data, this first one here, shipping data frame, and the index here is a receiving plant, a shipping plant, a mode of transportation. Remember, IM would stand for railway, TL would be for truckload, and then we have a transit time and an average rate, or the cost associated with each one of these. So every single one of these is an index, and then the different time and cost associated with it. The other thing we need here is material data. This is what's actually shorting and the demand for that material, and also how much we have in supply. So the next thing I'm going to pull in here is the material data frame. And as you can see here, our index is node. Notice it's not a shipping plant or a receiving plant. It's just any plant in general. What is the available supply? That is how much we're able to ship out. The projected shortage quantity. Think about this as the demands, or the excess demand, right? So demand excess to what we have in supply. How soon it's going to short, right? So this one says we need 50 units in 3 days, and then the daily shortage cost. So how we think about daily shortage cost is the total cost of that product, right? If we lose that sale completely, if we don't ship that product, we lose the sale. Going down here, the first thing we need to do is talk about some variables, right? Establish what those are. The two major ones we're using for this problem are shipment and shortage cost. So what shipment is actually a Pulp LP variable dictionary. And I'll actually show you what this is in a second. It's built of a receiving plant, a shipping plant, and a mode for every single index in that shipping data frame. So if I real quickly show you what that is, let me create another cell here. Shipments, right? And then I just want to see what one of these is. So if I copy this. So for example, one shipment might be from from shipping plant 1020 to receiving plant 1415 by way of intermodal or railway. Next would be a shortage cost, right? So what the shortage cost is again, the cost of not making that shipment. And again, this is another dictionary, and I have a formula kind of pre-written out here to explain what this actually does. So if material need in days, so how long we need to get this material before we short, minus the transit time, how long it's actually going to take to get there, right? If that is less than or equal to 0, then, right, we need to take the absolute value of that times the cost, right? And this will give us basically the shipment or the shortage cost. So I printed out already what that statement would actually look like. And to give you an idea of what a data frame object looks like in pandas, I'll print this again. Excuse me here. Just shortage cost. So as you can see here, for every single shipment, or every single shortage cost, there's a specific value associated with it, and that's what we're pulling from the material data frame. Delete that here. Now we begin the LP problem. This is where we establish the model, right? So we're using pulp again to do this. We name it right here. We're going to call this the cost minimization problem. And we're using LP minimize, because what we want to do is have the lowest cost possible. Now what we do in pulp is we add to the model. The first thing we're going to add is the objective function. And this objective function is going to be the shipment of that receiving plant, shipping plant mode times the rate of that shipment for every single receiving plant, shipping plant, and mode in our entire index that we created earlier. And that covers the first piece of all the different shipments that are possible. But the second thing we really need to add in is the cost of a shortage, right? So this again is the cost of that shipment, or not making it rather, times the shorting cost of that shipment, which we established earlier. Again, for every single receiving plant, shipping plant, and mode in our shipping data frame index. So now that we have our objective function, what we next need to do is build some constraints. This first one I wrote out some notes here. The first one means that any shipment from a lane must be equal to the demand, meaning demand must be satisfied. We don't want to short this thing. And the second one is shipment from any lane must be less than or equal to the supply at that node, right? So what this means is we don't want to ship more than we have available from an exterior node. And finally, what we get to here is the solution, right? And this is really easily initiated by model.solve, and we can print the status of the model. So for this specific case here, we have found an optimal solution. And here I just created a function to kind of visually explain what this solution looks like. And I created a data frame for the output. And what that looks like is something like this. So here we have our model solution, and we highlighted the optimal shipment here. That shipment would be to go from 1415 truckload to 1020 and ship the full 50 units from there. Now this shipment is actually going to be 2 days late, and the cost of that short is going to be $2,000, and the cost of that lane from 1415 to 1020 truckload is going to be $2,081. So what we did here was minimize the total cost of $4,081 down to $4,081 within all of our constraints. Again, here I just kind of printed out what the optimal shipment was, and this will be really important later on as we don't try and do this for just a single material week combination, but we do this for all materials over about the next month time period. Now what I'm going to do is actually rerun this thing with the timer and show you how quickly the model like this can run, because I think it's pretty impressive. So I'm getting rid of the commented outlines here. I'm going to restart the kernel here. This will clear all of the kind of preset work I've done. And then I'm going to run all. And you'll see we go down here. And in less than 2 seconds, we just executed all of that code, which again, I think is really impressive. When we talk about canonical form or kind of normal form of what was just accomplished in that less than 2 second time period. Well, we read the data frames, we created a minimization problem, and you can see it written out here, exactly what all was taken into account in this model. Subject to our constraints, right? I think it's 30-something constraints. 36 different constraints, and at the very bottom here you can see all the different variables that were taken into account as well. So again, less than 2 seconds to complete all this work, which I was very pleased with. Going back to the PowerPoint here, what we have accomplished so far and built into our model are the 4 different distribution centers, each of which can ship and receive products. We've accounted for 2 different modes of transportation. We have differing speeds of arrival for each mode of transportation, the option and cost of a stockout, and next steps, which don't have the green check marks next to them, will be including multiple weeks of requirements and including multiple products, right? So the company I work for has over 16,000 different unique products. And what we're going to do is account for those additional constraints and complexities in the next video. If you have any questions or feedback about the work, the project, or the code, please feel free to email me. My email address can be found right here. I also have a GitHub where I'm storing all this code and will be providing it to you all for free. So please check out my GitHub and I'll link that in the description below. Thank you so much for your time.